Hello everybody. So today we'll start section 3, the electric field. This is the last section for this chapter. So we'll talk about, give you some preview. So we'll talk about the electric field strength, how to figure out electric field strength. So the previous section we talked about electric force and compared with gravitational force. So both electric force and gravitational force are both field force, the same as electric force is similar to gravitational force. So so for example, if any object on Earth can feel the experience gravity, doesn't matter the objects on Earth or flying the airplane flying around of Earth, still in the gravitational field. The same thing. So the electric field has a similar property. So as long as a charge in an electric field, the charged particle going to experience the electric force. The second part we will talk about how to graphically represent the electric field. The last part we will talk about what's the electrostatic equilibrium and what's the properties of a conductor, full property of a conductor in a electrostatic equilibrium. Right, so electric field is something like gravitational, very similar to the gravitational field. Right, you're going to experience a force in electric field, a charged particle. The unit is Newton per Coulomb. So on next slide, I'll explain how to you can figure out the units Newton per Coulomb. So the direction of it, so this electric field is same as a gravitational field, is a vector. It's like any object on Earth or airplane, the direction always toward Earth, the bigger object. The electric field is similar like that. The direction is a vector, so it always has a direction component. We use a capital E to represent the electric field vector. The direction is the force exerted on a charge, a positive. So in this case, a positive charge. So if I have a positive charge, direction on the electric field could be this way, could be that way, whatever. The direction is always on the positive charge. So on the next slide, I will explain in detail.
An electric field is a region of space around a charged object in which a stationary charged object experiences an electric force because of its charge. The electric field at a point is defined as the electric force that would be exerted on a small positive charge, called a test charge, located at that point. The electric force, like any other force, is a vector quantity. The strength of the electric field at a point is defined as the magnitude of the force acting on the test charge divided by the charge of the test particle, which is always positive.
Okay, so if we use this definition, electric field equals of electric force divided by charge. So we have a force, the unit for force is Newton, the unit for charge is the coulomb. So we got the unit for electric field is Newton per coulomb.
The direction of the electric field at a point is defined as the direction of the electric force that would be exerted on the test charge.
Okay, so you can artificially put in this test charge in the field. For example, you have a positive charge. So how to figure out the electric field at this point? So you can artificially put a positive charge here, and think about the direction. The force is the same charge, so the force is the positive. So the electric field is the force, right? You artificially put a small positive charge here. So the direction for electric field the same the direction as the force. So point away from so the direction for the electric field for this positive charge is the point away from this positive charge. So if you have negative charge, so you're going to attract it to this positive charge. So this one is artificially, you can put in, imagine it. So the direction for the negative charge electric field is point towards it. Okay, right. So the strength of electric field, we can remember we talked about electric field is the force divided by the charge. So if you recall from section 2, electric force equals to Coulomb constant charge 1, charge 2 divided by the R squared, right? So if you divide this one by charge, or you can put charge 1, charge 2, so you can derive this one. So cancel out one charge. So electric field, the strength of electric field is Kc is Coulomb constant multiplied by the charge. This charge is the charge you want to figure out the strength of electric field divided by the distance. So what's the distance? You have a charge, right? You want to figure out the electric strength at this point generated from this charge. So the distance is the distance from the charge. You want to figure out the electric field strength to the point, because electric field, the strength depends on distance from the charge. So this position, this position, this position, for example, 1, 2, 3, the strength is going to be different for the 1, 2, 3. So it depends on the distance. So this is the distance between the certain point to the charge you want to figure out the strength.
Consider two small charges, one positive and one negative. Using the superposition principle, you can calculate the net electric field at any point. Choose a point P directly above Q1. First, calculate the electric field produced by each charge at point P, and then find the vector sum of these fields. Remember that the electric field at a point is the electric force that a small positive charge would experience at that location. The magnitude of the electric force exerted on the test charge by Q1 is given by Coulomb's law. Q1 and Q0 are both positive, so they repel each other. Since Q2 is negative, the force it exerts on Q0 is attractive. The strength of the electric field at point P produced by Q1 is the force divided by the charge Q0. The strength of the electric field produced by Q2 is found by an identical procedure. The forces on the test charge have been replaced by electric fields at a point in space. Now the x and y components of each electric field can be found separately. Then the components can be added to give the x and y components of the net electric field, which are shown here. These components can be added by drawing them to scale on graph paper. Each tote, the magnitude of the net electric field, can be measured with a ruler. The angle phi, the direction of the net electric field, can be measured with a protractor. Usually, however, the Pythagorean theorem and the arctangent function are used to find the magnitude and direction of the net electric field. The forces on the test charge have been replaced by electric fields at a point in space. Now the x and y components of each electric field can be found separately. Then the components can be added to give the x and y components of the net electric field, which are shown here.
Okay, so this test charge, positive charge, is imaginary. So it doesn't exist. So you can just imagine you put a positive charge there. So you can figure out the direction for the electric field. So it's positive, positive, so it's repulsive. It's negative, positive, so it's attractive. So we can use an imaginary test charge at a certain point to figure out the direction of the electric field. So it doesn't exist, all right? Imaginary. Right, so we can use example sample question to so you guys like numbers, so we can use some numbers to help you guys to understand it. So now we have a charge Q1. We know the magnitude of charge. It's small, like a U. Nu is a Greek letter. It means microcoulomb. So it's 10 to the negative 6. If you recall when we talk about the prefix, it's Q2, it's a negative charge, 5 microcoulomb, and the distance is 0.3 meter. Another one is on Y is 0.4 meter. So we figure out the P, the point at P. At this point, the electric field, because we need to use superposition principle we talked about in previous section. Right. So what do we know? We know the charge 1 positive charge, charge 2 negative charge, and the point distance from this point to the Q1 is 0.4 meter. To Q2 is 0.5 meter, and the angle theta is 53.1 degree. Right, then we can use the definition of electric field to figure out the electric field generated by Q1 and generated by Q2. So this one generated by Q1. Right? So this one generated by Q2. So Q1, you put Q1 divided by the distance R1, Q2 divided by the point, the distance between Q2 and this point in space. It's the Kc. You don't need to memorize this number. It will always be given. And plug in the Q1 distance, Q2 distance, you can figure out the strength, the unit is Newton per coulomb. However, this two number you don't know is the direction. You need to use the sign of a charge Q1, Q2. Which one is positive charge? Which one is a negative charge? These two, you need to figure out that. Then you can use it graphically to figure out the direction. Right, so in this case, Q2 is negative, so it's attractive. Q1 is positive, so it's repulsive. Right? So you need to draw this diagram to figure out the direction, because calculation, so it's a pure calculation won't give you the direction. You need to use a diagram to figure out the direction of electric field. Right, then we resolve electric field generated by Q1 to X and Y component, because Y, so X, because it's Q1 is on Y axis, so X component 0, Y equals to E1. This one is equal, right? Let me use a cosine sum function to figure out the X component and Y component. Why is so this one typo here? There should be 2. So it should be a Y component or E2. Right? So the direction here, this one positive, this one negative. You need to use diagram to figure out the direction of X and Y component. Let me combine to figure out the total component on X direction and total component on Y direction. So this one here, because this one is negative, so you need to subtract this one here, so that you can figure out X total, Y total. Right? Then you use the next step, use the Pythagorean theorem to figure out use the Pythagorean theorem to figure out this total electrical field, the strength. However, you still need to figure out the direction. This is only the magnitude, and the direction is use the tangent function. The tangent function to figure out the direction, this angle here. So use Y divided by X, tangent functions opposite divided by adjacent. So it's Y divided by X. If arctangent, you can figure out is 66 degrees. Right? So next part we'll talk about how to graphically or use diagram to represent the electric field. So we use the lens, number of lens, electric field, the lens here is the lens. We use the lens to represent the electric field, and the number of lens represent the strength. So for example, if I have a charge, for example, I just draw a little bit. So this is the first charge, the second charge, something like that. So this obviously this have more lens, some more lens. So this one is stronger. This one less lens. So this one less stronger. The electric field. We use the number of lens. Basically, the concentration of lens represent the strength of electric field. So electric field, remember we talked about electric field vector. So the electric field vector is always tangent to the electric field lens. So in this case, for example, if you have an electric field lens somewhere, something like that, the direction. So you need to figure out the direction of electric field vector at this point. So you just draw a tangent line here. This one is tangent, so this is the electric field vector at this point. So this here is a curve, is a line. The tangent of this certain point is a electric field vector direction. So we have electric field vector. We use the arrow E, Positive charge is just positive. Negative charge is negative. The line you still have direction. Remember, we talk about, so it's so on the following slide we explain the arrow, the direction of electric field line. You have examples. Oops.
Electric field lines are a way of visualizing electric fields. For an isolated positive charge, the lines originate on the charge and continue to infinity. For an isolated negative charge, the lines originate at infinity and terminate on the charge. When two or more charges are present, the field lines still obey the same simple rule. The number of lines leaving a positive charge or terminating on a negative charge is proportional to the magnitude of the charge. The third and last rule is that the lines of the same field cannot cross each other.
Right. So the electric field lines is always start from positive charge and toward the arrow, the direction of arrow is away from positive charge and toward the negative charge. So we have a positive, we have negative. Electric field lines, the direction is pointed toward the negative charge. So if you have both positive and negative charge, both positive and negative charge, between the positive and negative charge, it kind of start from positive, end up as negative. Right? You have the same kind of charge because it's going to repel each other. You don't have a closed line from positive to negative, so it's going to kind of repel each other. So all direct to infinity. All the lines kind of repel each other direct to infinity. The same thing, you have two negative charge. Same thing, you're going to towards the infinity. There's no closed, not like a positive and negative going to have a closed line from positive to negative. Right? This is the difference between positive and negative are same kind of charge. The difference between these two drawings.
For two equal and opposite charges, the number of lines that begin at the positive charge is equal to the number of lines that terminate on the negative charge. Near the charges, the electric field lines are nearly radial. The electric field is strongest in the region between the charges, which is indicated by the high density of field lines.
Right. Remember we talked about this line, the number of lines represent the strength because it's the same magnitude. Remember at the beginning of this animation, same magnitude of charge. So basically, if this 10 coulomb, it's a 10 coulomb negative. So the number of lines same. If you count this one, the number here equals the number here. Because in the middle is closed, so the same number. So both ends are going to the same number.
For two positive charges, the field lines originate on each charge and continue to infinity. Again, close to either charge, the lines are nearly radial. In this case, the electric field has a minimum in the region between the charges, which is indicated by the low density of field lines.
So this one, similar to the previous one we have for opposite charge, same kind of charge, you need to count the number. This part and this part should be the same number. So this is two charges have same magnitude.
If both charges are negative, the representation of the field will be similar, except that the lines will originate at infinity and terminate on the charges. The field created by a negative particle and a positive particle with double the charge resembles that of the equal and opposite charges, except that only half the lines originating from the positive particle terminate on the negative charge.
right? This one kind of typical because the charge different. So if you count for the positive, there's the number lines away from positive, so many number. So for the negative, it's only this part. Count this number. So the number of lines should be half end up on the negative charge. So this is double the number of lines away from this 2 plus 2q.
If the negative particle has twice the charge of the positive particle, the field would be similar. All you have to do is replace the direction of the field lines.
Right. So if we have a conductor in electric field, so if we have an electric field within a conductor, inside the conductor, the electric field inside conductor is 0. For example, we have a copper wire, right? Conductor. So all the electric field is within the this conductor, copper wire is 0. So inside is 0. All the electric field outside point away from this conductor. So why is like that? Because, for example, if I have all the negative charge, like electrons, negative charge within this conductor, because the same kind of charge are going to repel each other, so all the electrons, extra charge, going to be on the surface. Nothing within, because they're going to repel each other. So it's going to repel away, away, away. So we can draw this one. Have two negative charge, going to repel each other. So they have to move away until they reach the surface. They can no longer move. So all the charged particles going to be on the surface of a conductor. No charge within the conductor because of the repulsion between the charged particles. Because there has to be same kind of charge. Because opposite charge going to neutralize each other. So it has to be same kind of charge. So they're going to repel each other until all the charge are on the surface. So no charge within the conductor. So this all the charges going to be on the outer surface of a conductor. It's because the repulsive force between the same kind of charge. So the electric field direction going to be perpendicular to the conductor surface. So like I draw here. So at any certain point, this electric field, the direction is always perpendicular to the surface. So if I draw a circle, the direction always perpendicular to the surface. The direction it's hard to draw. So the direction always perpendicular and point away from, not always away, depends on the kind of charge. You have a positive charge, point away. So this is the direction of electric field. Right? So these are 4 properties you need to know. And the last one is if a irregular shape of conductor, like for example, you have a nail or something. You have a nail. Usually nail have a point, sharp point, right? Irregular shape, like something like that. So the charge tend to accumulate curvature, so at a sharp point. So this going to have more. So this charge can accumulate at sharp point here. Draw it bigger probably. So at the sharp point, there's a more accumulate more charged particles. If there's more particles, the strength of electric field are going to be stronger than like the here part. So this one is stronger. Here the electric field. So if you draw lines, So more lines, just going to be one line. So here, because it's flat, electric field strength much weaker than on the sharp point. Because the sharp point is more charged particles. So this is the fourth property you need to know. So because it's a repulsive interaction between the same kind of charge, all the charge is going to be on the outer surface. So that's why this inside the conductor, this electric field is 0. And this one you need to know is perpendicular. And the sharp point is the more charged particles accumulate. Right, that's all for this chapter.